Okay, so this is just to demonstrate a little bit more with a very specific example about what I'm talking about in terms of a computational study, a detailed study. So far in our exercises, we've reached a point where we're modeling volume, and obviously there's no real detail involved in modeling volume. We have a surface, and some of you people have played with a tool called Lunchbox for panelizing a surface, which is a really powerful tool, but sometimes can be quite difficult to control. So for me, the next step after thinking about the surface is really probably to return to what I call the system lines, and the surface gives us an idea of the overall form. We can do volumetric studies and general studies, but really to get into thinking about construction, we need to think about system lines. And in this particular model, which you can download from Secure, the system lines are used to generate the surface. So the first thing I'm going to do is delete the surface, and we're going to start to think about how we can start to model in more detail. And normally when we do this, you don't want to necessarily model every single panel all the way around the stadium. I like to set up a control method that allows me to select a specific zone within the stadium and start to work with that. Now, I should say that you don't necessarily need to follow all these steps, but you certainly need to watch the video to understand really what I'm talking about by a detailed computational study. So what we really want is we want to select a subset of these curves. So first of all, I'm going to switch them off because I want to see what the subset is. So to create a subset, we've got a component called subList, and that takes an initial list and a domain. And I want to create a domain which is basically where we're starting from, where we're ending. I'm going to do it in a way where we can control a slider, which I'm going to set to 12 as the start value, and another slider which is going to control basically the number of curves that we're going to pull out in that subset. And so by adding the start value to the number of curves, we get the end value. So that's 15. So we're starting at 12, adding 3, we get 15. We plug that in there, and you can see by using that, we can select a subset. So we're already zooming in on a particular part of the envelope for this study, and I actually want to set it so that it's on the other side. And you can see here it's nice and dynamic. We can move around the stadium, and this model is going to allow me to both refine the construction system, but also to test the methodology or the computational system for extracting the data from the model. So let's save that file. I'm going to save it as Aviva Panels. So we've got the subset of our curves there. Now I'm kind of making constant reference back to the original stadium. So we actually did something very similar to this, and we extracted between 3 or 4 bays at a time in order to share the data with the contractors, simply because the models were just so big once we got down to the level of detail where every single panel, every single bracket was modeled almost to the point where no detail was missing out. So each of these parts of the model became very large files, and just from the simple point of view of sharing them, emailing them, putting them on a server, downloading them, uploading them, we extracted around 32 or 34 parts of the stadium independently, and we're going to follow that kind of sequence here. But it's also going to allow us to think in much more detail, because we're not going to get bogged down with the processing speed of looking at a single piece like this. So the first thing I want to do with these is I want to offset them, because we have these our structural centre lines, and we're going to offset those curves, and we're going to offset them by, I think, about 400 millimeters. And what we're going to notice, although it's a little bit difficult to see, first of all, let's just do a divide by length on these newly offset curves, and we're going to put in 2000. And what we'll see here is some of them are offset on the inside, some are offset on the outside. So how do we control that? Well, there's an option here to put in an offset plane, and that's the way to control it. So we've got this, we should keep, obviously we should keep the model nicely organized. That should be called something like select sublist. Let's add that to it. Add that to the group. And then this offset I'm going to pull down here. So with this subset, if I copy that, right now it's taking in the curves, but if you remember this definition, each of those curves is based on a plane. So if we pull in the planes as well, we've now got a subset of planes that we can apply to this. And that now just helps us control the orientation of the curve offset. So you can see now the offset is all to the outside, which is what we want. And we're at 400 millimeters. That's fine. We should actually flatten this list here, because we just want a simple set of, it's a polyline curve, nice clean polyline that we've got there. And we've divided it up by 2000. So that's quite nice because it gives us different numbers of points on each curve, because the curves are all different lengths. And we can see that more clearly if we put on there a polyline. Now what we've got to remember at the moment, the organisation of this data runs with the curves. So if we want to run polylines in the opposite direction, we need to do something called flip matrix, which is literally going to rotate the storage matrix where those points are, so that we can connect up this point to this point to this point to this point, and we can try that to see. So if we do that, we've actually got a polyline that runs over the top of these curves, so we can't actually see it. But if we put the flip matrix in there, connect that up, we've now got equally spaced curves. Now what I actually want to do is I actually want to space them from the other end. Again, just referencing the original stadium process, so that we have a nice clean finish at this edge and we have a jagged finish on this edge. So what I'm going to do is there's another type of flip command, which is flip curve. So that reverses the direction of the curves, and you can see we get this nice, this jagged finish, which I quite like. Now the interesting thing is here we can play around with our little subset selector, and that allows us to increase the size of the subset, and interestingly we can keep on going. It actually allows us to go all the way around. Now we want to be on this side of the stadium, because we are, in this definition, we're dependent on, in a minute we're going to extract each of these parts of the polyline, and we want to organize the data so that all these lines are joined together. Now if we go onto the other side, that doesn't quite work as well. So one of the beauties of these kind of studies is that we can kind of avoid difficult data restructuring problems by choosing what part of the building we're looking at. But also we have to remember this building's symmetrical, so do we really need to generate the entire building, or should we really just be working on one half the building? So that's a big efficiency gain if we only have to generate half the building. So let's just have a look, and now we've got these polylines. We've got an error here because some of them down here, there's probably a point here and he's on his own, so therefore we can't make a polyline. But we don't need to worry too much about that, because we can clean up this data. So let's just have a look here. So keep this nice and organized here. So this is going to be given a name, scribble, so that's flip curves, divide curves, flip point matrix, and connect. So a nice long description, and I'm going to add that into the group. So right click, add, save my file, and